gentlemen, welcome to my talk, in which I would like to highlight a new possibility of fatigue testing on 1000 Hz testing frequency. My name is Markus Berthold. I'm the technical director of the company Rummel. We are highly specialized in doing resonance, magnetic, electromagnetic driven resonance testing machines, which are used for fatigue testing, high cycle fatigue testing, and very high cycle fatigue testing. In 5 years back, we could present the first prototype of our Gigaforte, a new testing machine that works on 1000 Hz testing frequency. We have now sold 5 machines of this type in the last 5 years. And yes, we all know that we should test more than 1 million or 10 million number of cycles in some cases. And thanks to the availability of fast testing machines working with the ultrasonic principle, there are also a lot of basic research activities took place in the last years. But there is an old question of fatigue testing, which gets more important in my point of view. What is the influence of the testing frequency on the fatigue life? And as well, of course, the size of the specimen can be a concern, particularly if you are looking on defects and inhomogeneous materials. So, in my talk, I briefly introduce the design of the machine, and then I highlight some frequency effects we have on test in fatigue. The capacity of the machine is 50 kilonewton, and we can also adjust the static load with a spindle, and the dynamic load is produced by electromagnetic drive. The vertical test space is a little bit limited if you compare it with conventional resonance testing machine, and also the stroke, the displacement is limited due to the high acceleration we get on 1000 Hz. Important is maybe when you want to have such a machine in your laboratory, the sound. You think about the sound. The sound is quite terrible. With 1000 Hz tone is not something you want to listen to the whole day. Here we see the principal design of the machine. The heart is this tube and this anchor, which work as a spring, which are accelerated with the magnet in the bottom, which is accelerating the base plate here against the side magnets. The specimen you see here on top, which is then on the other side, it's hole here on the crosshead, which is comparably quiet. Measuring of the force is a little bit challenging, 1000 Hz, due to the acceleration, and mainly, and of course also we want not to reduce the stiffness of the system. We have more than one load cell. One here for the piezoelectric load cell for measuring the dynamic portion of the load, and 2 strain gauge load cells placed in the column for measuring the static portion of the load. There is also a sensor to measure the dynamic displacement of the vibrating part, which works with a laser. Here on the table, one can put some instruments. This is not connected with the vibrating part, so here we can put a camera or a video extensometer, for example, or a heating system. We can use here common specimens that are type of specimens that are used for fatigue testing. Also small, it could be possible to test small, compact, stiff components as well. The limitation is the displacement, which we have to have in mind, and in case of damping, this can also limit the application of the machine. We have material with high damping. Now, I would like to share some information about the frequency effects that we may have to take into account. There is a nice work from Mr. Schneider from TU Darmstadt, where he tried to separate effects that he found in testing in different testing frequency. He used a servo-hydraulic machine working on 400 Hz and the 20 kHz ultrasonic testing machine. And he tried to divide the effects. On one hand, some which is really related to the material intrinsic effects, which are related to the strain rate itself, and on the other side, we could identify effects that are related to the environment, the interaction with the surface, with the environment. When we test material in inert atmosphere and in air, we find some differences. Very remarkable is this example in my point of view, where it has a much higher fatigue life when testing this quenched and tempered steel in different hardness. On the medium hardness, you can see a big significance effect of the testing frequency of fatigue life. Fatigue life is much higher when testing on higher testing frequency. The same behavior you could see found on aluminium specimen when testing in air, but not when testing in inert atmosphere, which we see here. And then, of course, the temperature and the heating up of the specimen is another topic. Now, the interesting question is what happened here with 1000 Hertz. Here we could do an investigation together with the Technical University of Osnabrück. We could do some tests at Rummel at 1000 Hertz testing frequency, and at Osnabrück they did tests on 20,000 Hertz testing frequency and on around 100 Hertz testing frequency with I would say a conventional resonance testing machine for Baru. And what we can see here that the difference, it seems that the difference between the testing on 1000 Hertz and around 100 Hertz testing frequency is not that significant. I had rather expected something, the result somewhere between, but it looks like they are in between the results that we get with 100 Hertz testing frequency. Here on higher load, I had some issues with heating up of the sample, so that may explain the lower strength that we measured here. I will show some more examples then indeed about the heating of the cell. But of course, it is only a few tests, and of course, it can be completely different for other materials. Here is another very interesting work, in my point of view, where Mr. Passoa at the Fraunhofer Institute in Dresden found some surprising results, that the fatigue life on higher testing frequency is less, and this what could be correlated with the formation of the strain-induced Martensite antibodies. It seems to be also be related to the testing frequency. But the most significant effect is probably the heating up of the sample. With every cycle, and especially if there is some small portion of plastic deformation somewhere in the material, then this damping is then dissipated to heat in this, and we see that in a temperature increase. The higher the frequency, the more heat is produced per time, of course. We see here that with increasing load, the temperature is increasing. Here, this is the temperature, the green plot, and the temperature increases with increasing load. But we also can see that here with compressed air, we can, in this case, we can control the temperature quite well, and continuous testing is possible. There are other materials where the heating is not an issue. Here is an example of a high-strength bolt where we could test on quite high load, where the life is below 200,000 load cycles. And here we see the green plot, again, the temperature, and the heating up is negligible. So it can also be interesting for some components and parts where we can reduce the testing time dramatically. So if I summarize, so our new testing machine is an interesting tool for doing investigation, especially in the very high cycle fatigue regime. We can use common specimen types, and of course, depending on the material, we have also to look on the heating up of the specimen. But usually compressed air cooling is sufficient, and continuous testing is possible. And I'm very optimistic that this testing machine helps to better understand frequency effects and to increase the confidence in our fatigue data that we receive. We have plans to do more testing, especially with these high-strength steel bolts, to evaluate if there is any effect on the results by the higher testing frequency. And we want to do testing on fiber-reinforced material in the very high cycle regime, where the heating up of the specimen is not significant, together with the Technical University. With that, I'm at the end of my talk, and I would like to thank you for your